Hello everyone and welcome to today's Living Lab lecture. My name is Josephine Umloft. I'm a seismologist and I work at ScaDS, where I use machine learning and seismic signals to better understand near-surface environmental processes. And in particular, I'm, as you can see, interested in glaciers, especially in glacial dynamics and in the mapping of glacier sliding. At first, I want to briefly introduce glaciers and the relevant processes and signals of interest that are relevant for our study. Then introduce the site, so the study area and the data that we are using to you. As a teaser, we will be on Glacier Argentière today in the French Alps. And finally, the third part will be on the machine learning. We are using an XGBoost model here. I will briefly introduce the method, but spend most of the time on explaining how we pre-process the data, how and which kind of features we derive, how we harmonize everything because it's a multi-scale data set, then interpret our results and evaluate them. And finally, we will also look at the feature importance to make everything a little bit more explainable. Okay. So glaciers in general are quite complex. Some of you might have been on a glacier before, and you might have noticed that there's quite some noise going on, which is due to rapidly changing weather conditions in these high mountain areas. Then we have crevices opening and closing, which generates this cracking that you can hear acoustically. Then there's water flow, especially during the melt season. So during summertime, water can flow on top of the ice, within the ice body, or at the ice bedrock interface. And finally, we also have the sliding of the actual ice on the glacier bed, so on the bedrock. It's what we call the glacier bed. And we call this stick-slip sliding, or so-called stick-slip ice quakes in seismology, which is basically like an earthquake, but in the ice, generated by the movement of the ice itself. Okay, and we can measure those signals, as you can see here on the upper right, these impulsive icequake signals using seismometers in the field. We can also acquire GPS movements, GNSS data, which would give you the velocity of the ice on the surface. And we also acquired meteorological parameters here, as the weather conditions, as I said earlier, are changing quite rapidly and are very relevant when dealing with ice. Okay, but the problem most of the time is that those ice quakes are difficult to observe, difficult to find, in fact, because they are often hidden in a very high noise level due to all these other environmental noise sources that happen side by side, often in similar frequency bands at the same time, very close to each other. So we might not see the actual signals that come from the glacier bed. So now you might ask yourself, okay, if we have GPS measurements on the surface of the ice, which gives you the velocity, as I just said, and if we are interested in glacier sliding, why caring about seismology at all? So that's what I will show you in this lecture series, what rich archive seismic data is to better understand processes in high spatio-temporal detail, and in particular, in our case, to infer for signals that come from the glacier bed. So overall, this glacier flow that we are interested in is a combination of internal deformation of the ice and basal sliding, so the actual sliding of the ice on the bedrock. And the big problem here is that we still don't have a good physical model that we can also use for predictions and forecasting on a high spatio-temporal resolution. Okay. Let's have a look at the data and the site. What you can see here is the Argentière Glacier, located in the French Alps. And in course of the Resolve project, led by ISTER Grenoble, we installed a multi-physics instrument platform here on this glacier and in the surroundings. So what you can see here is seismometers, for example, the white triangles. Then we have GPS stations, which are the red triangles. There's a weather station here measuring precipitation, temperature and air pressure, for example. Then also runoff, so the water discharge, what is actually melting, is measured here at this green circle. And we also had a bicycle wheel beneath the glacier installed to actually measure at this specific point in this cavity the velocity of the ice at the base. Here's what this looks like. This is a seismometer set up in the field. The seismometer itself is buried. The sensor, which measures elastic waves traveling through the ice and gives us the ground velocity. And you need some additional equipment here besides the sensor, like batteries, digitizers, and a GPS antenna. And here's the wheel that I just mentioned, the bicycle wheel, which you can see here installed really at the bottom of the glacier. So we are looking now from the bedrock up to the glacier and to its bottom. Of course, those areas are very limited, so we cannot do that on a regular basis. So this is really a very exceptional case here and very interesting to see this data. Okay, and what we derive then from this multi-physics, multi-instrument platform is all these parameters, as I just introduced, meteorological parameters like air temperature and precipitation over time. We can see here month of the year between 2017 and 2018. We see the seismic power of one seismic station and also the water discharge here in blue, and you can already see that there's some correlation going on. And we can also see the data from the bicycle wheel, some data gaps, as it was not functioning all the time, which has more and less active moments, and also somehow correlates with the water discharge and the seismic power. Okay. In our study, we will focus on a very small portion of this database, and I will show you why this is. In this period here in May 2018, we had on top of the setup that you have just seen a very dense array of seismic sensors. So we have not only 7 stations anymore, but a very dense grid-like array of 100 nodes. And why is this important? Because arrays, especially dense arrays, provide very valuable spatial information, because you can locate the sources, so where the signals actually come from that we measure using the seismometers. And this is of special interest for us because we are interested in sliding, and we want to of course model this, but also understand our model better, and in best case scenario find active regions, active areas in the glacier that are relevant for sliding. So this is a very unique data set and archive here, which we use to train our model. Okay. So we are using an XGBoost model here, so gradient tree boosting, which is based on decision trees and random forest, while we have a continuous update here on the arbitrary loss function to make the model more robust and better. And what we use as input features here is seismic data and meteorological data. And what we want to predict here, so what our label is the GPS velocity. So we want to find the underlying function between the GPS velocity and the feature space. So here's what this looks like. So we have the XGBoost model using this database here. As labels, as I just said, those red triangles are relevant here, the GPS stations, which give us the on-ice surface velocity. And as features, we use meteorological parameters from the weather station over here, statistical features from the seismic stations, and here we only pick a few of individual seismic stations to do that. And finally, we used the entire array, all the 100 stations here installed in the ablation zone of the glacier to derive seismic source locations. I will guide you through this briefly. So as meteorological parameters, we use the air temperature, the precipitation, and also the runoff and the water discharge. Statistical features here, we calculate the standard statistics from our time series using a sliding window approach, like the mean, the standard deviation, variance, kurtosis, and different quantiles. And here's how we do this. We have our seismic signal of one station, of one representative station. You can also use multiple in agreement with the dimensionality of your feature space. And we use this sliding window approach, meaning we walk over the signal, and for each window we compute the statistics, and with an overlap of 50% we then go to the next window. Okay, and finally we use these seismic source locations. And how are we doing this? We are using an approach here that is meanwhile quite common in seismology. It's called match fit processing, which is a type of beamforming. And this method reveals the location of a seismic source by correlating, or you can also call it matching, as it's implied by the name, the seismic records that we acquire on the field with synthetic waveforms based on an underlying grid to find the source location of a certain waveform. So we have on the one hand here our field observations. Here you can see a seismometer, so the sensor itself installed on the ice in the field. And we have these sensors 100 times, as you saw before. So what we're going to do is that we compute the cross-spectral density matrix of all sensor pairs, while I would be sensor 1 and J sensor 2. And for a certain frequency, or you can also do that for a certain frequency band, we correlate the spectrum of one station with the complex conjugate spectrum of another station. And that we do for all station pairs, and that kind of gives us the representation of our measured wave field in a certain time window for a certain frequency band that we measure in the field. And on the other hand, we generate synthetic waveforms. This can be done in simple ways, but also in very complex ways. We decided to use a simple phase term here to compute our Green's functions, or our wave equations here, which is basically a phase. So we do not include any amplitude information, which would make the problem more complicated, because amplitudes are characteristic for different wave types, and by doing this you would favor different types of waves, and we want to have our search very open and basically consider all processes, meaning also all signals that are generated. So what we have here is a 3D grid where we systematically place synthetic so-called candidate sources into this grid. And from each grid node, we compute this synthetic phase here, also dependent on the frequency and on the distance towards each station. So that's how we generate our synthetic wave field for the entire array setup. And we do that for each candidate source position and for all relevant frequencies, and of course for all synthetic source receiver combinations. Also here we derive a spectrum, and what we then do is that we match both fields, like our field from the cross-spectral density matrix in the spectral domain, and also the synthetic wave field at each grid node. And we do that again for each of the positions in the grid, and by doing that we kind of test which of the synthetic waveforms from a certain candidate source position fits our true field observations best. And the position with the maximum correlation between the field observations and the synthetic waveforms would give us the most probable location of a source in the field. Exactly. And here's a snapshot of the catalog that we computed to derive seismic source locations. So we applied matched field processing to the entire month of data that we had with a resolution of 2 seconds, meaning that we investigate each 2-second long time window during this month independently and for multiple frequencies. And for each of these time windows, we compute the seismic source. So what you can see here is a snapshot for 1 hour with, again, the temporal resolution of 2 seconds for a frequency of 10 Hertz. So you can see this is quite some information that we have here then during the entire month. And you can already see some structures here in these point clouds. Those are probably related here to water flow. On the bedrock, you also have some activity, but it's really hard to guess anything related to sliding. While you also have a lot of activity on the ice surface itself, which is only natural because our sensors are at the surface, so they are most sensitive to processes that actually happen on the surface. Okay, and finally, our labels. These are on-ice surface velocities acquired by the GPS stations in the field. Here, the red triangles. In total, we had 7 stations, and each station measured 3 components of motion, the northeast horizontal directions, and also the vertical component. Okay, and as I said in the introduction, we have a multi-scale problem here, and what I mean by that is that all our features and also the label have different temporal resolutions. So the meteorological parameters are sampled at a 10-minute interval. Statistical features, as we use our sliding window approach, directly match to the on-ice surface velocity because we could guide that by ourselves. So they have a 1 hour timestamp, and the seismic source locations, as we want this to be really highly resolved as processes and dynamics change so quickly in the ice, and we want to capture this, have a resolution of 2 seconds. So what we did is that we harmonized all features to match this 1 hour timestamp, and in particular, for the seismic source locations, we tried different things here to still keep this valuable spatial information that we have, and not just downsample downsample the data to this hourly timestamp. So what we did is that we defined 8 different regions in our glacier. So we voxeled the glacier, and for each voxel we count per timestamp and per frequency the amount of sources which we in the end use as features. So that number in the end would be our feature, and a higher count would equal more activity in the glacier. At least that was our hope in terms of representation and how we can use these extensive spatial information very highly resolved as features here. Okay, and finally, we have this nice harmonized set of features here, just some examples for some frequencies and some parameters. You can see here the velocity of the GPS on top. Some were installed on the ice, some were installed on bedrock close to the ice. We have precipitation here in green, the air temperature in red. And then we have the different statistical parameters here, like the quantiles, for example, kurtosis and variance. And we also have our beamforming information, so the matched field processing located sources, which we count. So here you can see an output for one of the voxels and one frequency band. Okay. Finally, we actually train the model. And here you can see different outputs for different types of splits that we tested and used. So the first example here would be a random split. So what you can see here on the y-axis is the velocity given by our label, which is the GPS velocity in millimeters per hour. And here you have the time, which is approximately 800 hours during this 1 month in 2018. And if we apply a random split here, you can see that data and model match nicely. We have a correlation coefficient of more than 80%. However, this is kind of a trivial task because we don't have any prediction horizon here. We simply go from one sample to another, but what we want to have actually is the longest prediction horizon possible, as we want to predict glacier sliding. What we then did is a 50-50 split to make the task more hard, but also to go into the direction what we're actually interested in, meaning the prediction. And you can see here that for training this works pretty good, while for testing we are quite off with a correlation coefficient of 30%. This is worse than random, so this is also not really helpful. What we then came up with is testing different blocks, or defining different blocks in our time series for training and testing. And here you can see two different models using these blocks. One has 36-hour-long blocks, the other one 96-hour-long blocks. And you can see in both cases we have a reasonable high correlation coefficient, or RMSE, almost similar. So what we then did is to look at the robustness of our model. And what we did here is that we kind of tested the performance stability against smoothing, so smoothing our time series. And you can see here indicated by those different colors all the different types of split that we used, from random over 50-50, 80-20, to differently sized blocks from 24 to 96 hours. You can see here the correlation coefficient here, the RMSE, which is inverted, of course. And then you can see the rate of smoothing that we applied to the time series or to the feature space before training the model and testing. And you can see that for random, anyway, the correlation coefficient and RMSE are not adequate, not what we desire. We have quite a good performance for these 24 and 36-hour-long blocks here, the green graphs, while we have a quite low performance for 50-50 or 80-20 splits. So what you want to do is stick to these block model, because they seem to be performance-wise good, but also quite robust against smoothing. And we kind of tested how far we can go here. And you can see that if you have a model of 96 hours, even though you have sometimes these very high correlation coefficient or reasonable high correlation coefficient, sometimes they are very low, which indicates that the model is not really robust and stable. Doesn't really learn and is not really able to generalize, let's say. Okay, but we are quite confident and happy with the 36-hour-long blocks. So what we also did here is to look at the hyperparameters and did quite an extensive hyperparameter optimization here for all these different kind of splits. And here again, you can see that there's quite some fluctuation going on for these different kinds of splits. So there's not really an indication for going into one direction or the other. That's why we mainly focused on the performance together with the robustness against smoothing. But what this also shows you is that whatever kind of model you use, you have to optimize for the hyperparameters because they differ so much for these different kind of models. And my guessing would be that this is also the case if you apply this model to different kinds of data from different glaciers. Okay, so finally, we end up using this 36-hour block model, which is quite convenient because we have performance of RMSE 0.64 and a correlation coefficient of 83%. You can see that the model is able to capture the overall trend, of course, so the long-term variations nicely, but also these short-term fluctuations, which was really surprising to us. And with a prediction horizon of 36 hours, that's in case of a massive sliding event, of course something that would be helpful. We are not here yet. Just let me state that this is the first study here of this kind. But we will apply this to other types of glaciers, of course, and test the robustness. Okay, and finally, we also had a look at the feature importance. This is actually something that interests us the most. And what you can see here are SHAP values, meaning we order the features by importance for the model to take its decision. And what you can see here in the upper part, you have these V1, V3, and V2 features, kind of cryptic probably now, but they stand for the beamforming, for the match fit processing features, meaning V1 would represent source locations in voxel 1, here at the bottom of the glacier, in the frequency of 5 Hertz as a sum of all the sources that are captured within this voxel. And you can see V1, V3, and V2, they are all bottom voxels. So what this tells us, and this is really exciting for us, is that the activity at the glacier bed is most important for the actual sliding velocity on top of the ice, here measured at these red triangles. So coming back to what I just said in the introduction, we can see here that glacier sliding is modulated by activity on the glacier bed, and we can use seismicity to infer and find or to actually find the areas within the glacier that are active and that are responsible for sliding. And with this, I want to thank you very much. I hope you heard some interesting things about glacier sliding and the field that we are working in. If you're interested or if you have any questions, feel free to contact me, and thank you very much.